Before bones, before leaves, the planet already breathed chemistry. Black oceans rolled beneath a copper airless sky. Lightning stitched the darkness above newborn seas. Volcanoes glowed where continents had barely begun. Nothing here has eyes, teeth, or footsteps. Yet something astonishing is already alive. The first creatures are smaller than dust. They will change every ocean, every cloud, every future. To find them, we must read stone-like memory. And the oldest chapter is almost erased. Earth formed about 4.54 billion years ago. Its surface was violent, molten, and unstable. But violence was not endless. Ancient zircon suggests liquid water appeared surprisingly early. By 4.4 billion years ago, seas may already have existed. That possibility changes everything. Life needs somewhere to persist. Water gave chemistry time, movement, and memory. Even the Hadean may not have been constant hell. Catastrophe came in pulses, not forever. We still do not know exactly where life began. That mystery remains one of science's deepest. Some scientists look to deep-sea hydrothermal vents. Others study tidal flats, pools, and shorelines. Both ideas share one requirement. Energy had to meet simple molecules again and again. From that meeting came metabolism. From metabolism came inheritance, selection, and survival. Somewhere in deep time, chemistry crossed a threshold. It began copying itself imperfectly. That single step changed Earth's future completely. Matter started remembering what worked. The first creatures were not animals. They were single cells or something very close. No fins pushed them forward. No jaws opened. No voices ever called. Most likely, they lived suspended in water. Entire worlds fit inside a single droplet. They fed without sunlight at first, perhaps. Chemical gradients may have powered their tiny bodies. Hydrogen, iron, sulfur, and carbon dioxide mattered. These were the ancient currencies of life. Scientists use one name for our shared ancestor. LUCA was ancient, but probably not first. LUCA means last universal common ancestor. All life alive today seems to pass through it. Some reconstructions place LUCA near vents. There, hot water met cold sea in endless reactions. Seawater and rock reacted constantly there. New compounds formed every second without pause. In such places, warmth met chemistry. Tiny cells could harvest that difference for energy. Scientists sometimes compare these systems to batteries. Life may have learned to tap them. Yet certainty always stays just out of reach. The oldest rocks were baked, folded, and altered. Earth recycles its surface relentlessly. Early evidence survives only as scarred, precious fragments. That is why the beginning feels ghostly. We are chasing shadows impressed inside stone. One candidate comes from Greenland. Layered structures there may be 3.7 billion years old. Another comes from Quebec. Vent-like rocks preserve possible microfossils at least 3.77 billion years old. Those finds are thrilling. They are also debated. Deep time rarely speaks clearly. Less controversial evidence appears a little later. By 3.5 to 3.4 billion years ago, life flourished. In Australia and South Africa, ancient rocks hold signatures of microbes. The clues repeat across continents. Not shells or skeletons, layers, textures, carbon traces, and microscopic forms. Sometimes shape alone is not enough. Scientists want chemistry, context, and several clues together. The planet's first living record is humble. It looks more like patterned stone than life. Some of those patterns were microbial mats. Countless cells carpeted wet surfaces together. They trapped sediment as water moved. Grain by grain, their tiny empires thickened upward. Over time, the mats built domes and ridges. We call those stony mounds stromatolites. Even now, stromatolites still grow in rare places. Modern examples help decode the ancient ones. In cross-section, they show fine layers. Those layers record communities growing toward light. Imagine a shoreline without moss, trees, or animals. Only films of microbes glistened there. Waves washed over them every tide. Sunlight flashed across slick living skin. The smell would have been startlingly alien. sulfur, salt, hot minerals, and no flowers. The sky looked different too. Oxygen was scarce and haze was likely common. You could not breathe here. Modern lungs belonged to a much later Earth. But these microbes needed no breath. Many thrived in oxygen-free waters and muds. Some likely fed on pure chemistry alone. Others eventually learned to use sunlight. Before oxygen-making photosynthesis, other versions probably existed. Light could power life without changing the sky. Then came a more radical trick. Certain microbes began splitting water and releasing oxygen. That invention was revolutionary. It turned daylight into stored chemical energy. Photosynthesis did not green the world overnight. It began quietly, inside microscopic cells. Cyanobacteria are famous with this power, but their earliest timing is still carefully studied. What matters most is the consequence. Tiny cells started changing planetary chemistry forever. For ages, oxygen they made did not linger. Iron and other substances soaked it away. Oceans became chemical battlegrounds. Invisible waste met hungry minerals in the dark water. Rust began appearing through ancient seas. Vast iron layers still remember that transformation. Those banded rocks are fossilized consequences. The water itself was changing character. What looks like ordinary stone today once marked revolution. Entire oceans were shifting color. All of it happened microscopically, yet nothing larger would exist without it. Every fish, fern, dinosaur, whale, and human owes a debt here. This is the first inheritance. These were Earth's longest rulers. For billions of years, microbes were almost everything. They spread through seas, sediments, bents, coastlines, and crust. No predator stalked them. There were no forests to shade them. No birds crossed the open sky. Even continents were different actors then. Small crustal blocks drifted through dark oceans. Day after day, tides advanced and retreated. Microbial films endured, divided, and returned. Storms could strip whole mats away. Life simply rebuilt itself, cell by cell. At night, the shore would not fall silent. Chemistry kept working in darkness. In the shallows, bubbles may have gathered. Beneath them, billions of cells divided unseen. If you saw this world, would you recognize life? Tell me below. Could you survive one shoreline here, or would the air defeat you first? Hold that thought. The strangest planetary change is still coming. Oxygen slowly escaped its chemical traps. At last, it began accumulating in air. Around 2.4 billion years ago, Earth crossed a threshold. The atmosphere changed. This is called the Great Oxidation Event. The name barely captures its strangeness. For oxygen-breathing life, it sounds like a gift. For many earlier microbes, it was poison. Some lineages vanished or retreated underground and underwater. Others adapted and flourished. Life remade itself without a single roar. The greatest turning point was invisible. Oxygen also changed the sky. New chemistry helped form an ozone shield above. That shield mattered profoundly. Surface life became safer beneath sunlight. Methane likely declined as oxygen rose. Climate and chemistry shifted together across the planet. Much later, more complex cells appeared. Eukaryotes carried internal compartments and new possibilities. Their exact origins remain complicated. Partnership and merger seemed central to the story. One ancient cell likely took another inside. Instead of digestion, the partnership endured. That captured micro became mitochondria eventually. Available energy suddenly scaled upward. Later, in some lineages, another partnership followed. Chloroplasts arrived, and sunlight gained new forms. But all of that comes much later. For most of Earth's story, microbes stay center stage. If you walked through those eons, landscapes would seem empty. They were never empty. The drama happened at tiny scales. Membranes, minerals, molecules, pressure, and light. A grain of sand could hold multitudes. A drop could host civilizations. We usually picture first life as primitive, and endurance it was astonishingly sophisticated. Some descendants endure extreme heat today. Others tolerate salt, acid, darkness, or crushing pressure. That endurance hints at ancient roots. Early Earth rewarded flexibility more than elegance. These cells survived impacts, volcanism, changing seas, and chemical upheaval. They outlasted worlds within the world. Their bodies were tiny. Their influence was continental first, then global. Even today, their descendants dominate the unseen Earth, beneath us, around us, within us. The oldest creatures never truly vanished. They multiplied into every later age. Dinosaurs were spectacular newcomers. Microbes had already ruled for billions of years. So are mammals, birds, and us. We arrive near the closing seconds. This is the hardest lesson of deep time. Greatness does not require size. The first creatures left no footprints, yet they rewrote ocean and atmosphere. They left no bones in museum halls, yet every fossil display depends on them. Even the word animal depends on them. Oxygen made complex movement possible. Every breath you take echoes their labor. Every green leaf repeats their experiments. And still, the beginning stays partly hidden. Scientists argue because the evidence is precious. One structure may be biological, another may be shaped by chemistry alone. That uncertainty is not weakness, it is how honest science sounds. The oldest chapter deserves caution. Extraordinary age demands extraordinary proof. Researchers look for several signs together. Shape, chemistry, setting, and repetition strengthen the case. Still, the broad picture is secure. Life appeared early and it appeared microscopic. It likely arose on a young, watery planet. Then it persisted through turmoil. From there, evolution never stopped experimenting. Every future body plan waited downstream. Eyes wait downstream, wings wait downstream, so do your hands. Before all of them came membranes. Before hunting came chemistry. Before song came copying. Before teeth came time. That is why these first creatures feel almost mythical. They were tiny, but world-making. Not gods, not monsters, just cells enduring. Cells that turned barren water into a living planet. Cells that made later wonder possible. When we search Mars or icy moons, we carry this lesson. Life may begin small. We should not expect thunderous entrances. The first signs may be stains, layers, and chemistry. That makes the universe still quieter. It also makes it feel fuller. Somewhere else, a world may already host its first creatures. We may simply overlook them. Back on Earth, their descendants still shine in tide pools. They still bloom around vents. The oldest story never ended. It is still metabolizing around us. And we are late arrivals. We inherited a planet already ancient. For almost all of Earth's history, nobody looked up. Yet life was busy becoming. Oceans changed first. Skies changed next. Everything else followed. That may be the deepest wonder here. The first creatures were enough. Enough to change oceans. Enough to change skies. Enough to make us. What do you think Earth's first shoreline felt like? Tell me below. Subscribe and ring the bell for more journeys into the lost world before us. We are young, but our origins are unimaginably old. The first dawn still lives. In every breath, the ancient ocean returns, and the smallest pioneers still speak.